Hey, welcome to the session on experiments with TensorFlow. As part of the first session, we will be building CNN using TensorFlow 2.0. We will be using the Google Colab environment to develop this particular experiment. We will be using the following dataset to develop this particular experiment. This dataset has been referenced in this particular notebook. There are two parts of the data. One is the metadata and the other is the actual poster images that we need to go through and identify the respective genres of that particular movie. If you are not familiar with the concept of convolution and pooling, I would request you to go to this play notebook that gives you a perspective of how convolution and pooling works. It also gives you a step-by-step introduction into how convolution and pooling works. On top of that, I would also recommend that you go through the Andrew Ng deep learning AI videos that gives you a very good perspective of what is convolution and pooling. The playlist is very long, but you can hop onto this experiment once you are done till this particular module called C4W1L11, which ends with why do you need to do convolutions in the first place. So this experiment is built on TensorFlow 2.0. If the current version is 1.14, I would recommend that you uninstall the current version of the TensorFlow and reinstall TensorFlow GPU, which is what we are going to use for this particular experiment. So once the TensorFlow GPU is installed, it will prompt you to restart your runtime. So please do click on Restart Runtime. And once you click on Restart Runtime, you can cross-check by clicking on the runtime, change runtime type to see if you're running the Python 3 GPU version. So there are two parts to the data. One is the metadata and one is the poster data. The poster data is relatively a large data set. The best way to access this data set in Google Colab environment is to upload your data to the Google Drive. And this is exactly what I've done in my Google Drive, that I've uploaded both the poster data and metadata to my Google Drive. Now I'm going to connect my Google Colab environment to the Google Drive so that I can download the data directly from the Google Drive to the Google Colab environment. So before I start downloading the data from the Google Drive, I need a couple of libraries which I'm going to import it into my environment. And we'll focus on some of these libraries very soon. So the first thing that I'm going to do is I'm going to import my drive onto the Google Colab environment. And as you can see, it is asking for an authorization code. I'm just going to click on this particular link, do the sign in, go to the stubs, and then it is going to give me a code, and I'm going to copy and paste this code onto this particular text box. And once I am done, it has essentially connected my Google Colab environment to the Google Drive. So let me just run this particular statement to give the listing of all the data points which are located in this particular folder that I have placed in. And as you can see, I've got both the poster data as well as the poster metadata being placed in this particular drive, which I'm able to access it directly from the Google Colab environment. The Google Colab environment has got a temp directory. I'm going to create a couple of folders in the temp directory so that I can download the respective files from the Google Drive. The first directory that I'm going to create is the metadata dir, which will hold the metadata that I'm going to download from the Google Drive. And I'm going to give the local zip file, which is the zip file, which is the movie poster metadata.zip, and I'm going to zip it and place it inside this particular folder using the zip command. And as you can see here, once I run this particular command, I should be able to go and look at the file section and look at the temp directory to see if that particular file has been zipped and placed. And as you can see here, I've got a movie poster metadata directory and there's a ground truth directory. And then these are the files which tells you the list of movies from 1980s to 2015 which we will be accessing to build the database. Now I'm going to make a list of all the files in the ground truth directory into a single consolidated file called the file list.txt. Once I run this particular command, it is going to give me all the files which is in the file list.txt, and then I'm going to build a list which contains all these particular files. And as you can see here, I open the file list.txt and I append it to the list object called the file list. And as you can see here, there are about 36 files in total which talks about all the movies from 1980s to 2015. The next step that I'm going to do is I'm going to download the data, which is the movie posters data at this point in time. So as you can see here, I have given the name movie posters dir. I'm going to run this particular command so that it creates this particular directory. And same as before, I'm going to download this data file which is called the movie poster data set.zip onto my local drive. I'm going to unzip it and I'm going to place all the posters into this particular directory called the movie posters data. And once I do that, so now it is done. So let me go and check if it has already done that particular work. And as you can see here, there's a folder called the movie posters data. And within the movie posters data, there's a movie poster data set again. And within that particular data set, we have several folders. And starting from 1980s, so you have a list of files and that particular reference to the movie poster images. So I'm going to create one more directory called the all movie posters data dir, which is going to be the consolidated placeholder for all the movie posters. Once I create that particular directory, I'm going to parse through each of those files and understand how many entries are there in each of those files. And as you can see here, 1982 year doesn't have any files in them. So it's time to consolidate the data points into a data frame. So I've created something called a movie list database, and it is going to have movie year and the movie poster count. And this particular data set is going to be used downstream to filter out those data points which are non-existent. So as you can see here, 1982 doesn't have any data files. And there are about 8052 movie posters which are available. Now it's time to build the actual database of files. So here's a quick and dirty version of reading the corresponding metadata files. There is some certain difference in terms of reading the files prior to 1982 and files after 1982. So they use different encoding. So I created this quick and dirty version of reading those files, and as I said, this is not the best code but serves the purpose of collecting relevant information. So as you can see here, I'm going and iterating through each of those files, and I'm collecting certain information like the year in which the movie was released and so on and so forth. So I'm building a dictionary object which contains all the data points. So all the data points are in separate files. I'm consolidating them into a single file structure. So let me run this, and as you can see here, I have created something called a movie list, and within the movie list I have added all the information that was present in the metadata. Okay. Now let's check on the length of the movie list, and you will see there were 8,760 files or 8,760 movie references, but prior to that we also saw that there are only 8,052 movie posters. So there is some kind of data anomaly which we need to sort it out. So let's take care of the data anomaly. We will run through the master movie list, and for each movie there is a file that is being referenced, and we will check if that file is existent in our temp directory. If it is existent in our temp directory, we will add that movie to the scrub movie list, which is going to be the list of all movies whose files we do have in terms of the posters. and that will be the step 1. So once we run this particular code, it is going to move all the files of the movies, the poster files, into the directory that we had created earlier called the all movie posters data. And now let's check the length of the scrub movie list. And as you can see that we have 8052 movie files, which is same as the earlier number that we had observed in terms of the number of poster images, which is 8052, and which means that we have taken care of the data anomaly at this particular point in time. So let's go ahead and build a data frame which has got all the list of files and its respective genres. So as we can see here, we have created a data frame called the movie list database, and then let's run it and let's get a view of what the contents are. So for each file there is the respective genre. So this data frame is going to be served as an input to the TensorFlow. But in order to be served as an input to the TensorFlow, we need to convert all the genres listed here, correct, in each of the data point. We need to convert it into a list object so that the TensorFlow recognizes that these are the classes that we are looking to learn and predict. So we are going to use something called the lambda function, and we are going to apply the lambda, and as you can see here, I'm going to split by comma, and then I'm going to convert each of those elements into a list object. So let me quickly run it here, and then as you can see here, after the run, that each of the entries that you saw earlier has been converted into a list object, and so does the same for all the data points listed in the movie list database. So as a first step that we are going to do is we are going to pick one genre for each movie. So instead of having multiple genres, we are going to reduce it to one genre. So I'm creating a new data frame called a movie list database one genre, and I'm going to iterate through each of these genres wherever there are multiple genres. I'm going to pick one of them, correct? And then what I'm going to do is I'm going to divide the data into a trained data set and a validation data set. And the way I'm going to do is by doing some analysis here. Let me quickly share with you in terms of uh, the distribution of the data point, correct? And then so this is your stats, and then let's have a look at it. And as you can see, there are the following are the genres and the distribution of data as by this genre. We're going to sort this particular data set, and then what we are going to do is we are going to get the top 10, correct? And so I have already sorted it now, and as you can see, I'm going to get any genre which is having at least 100 entries, and that is going to be my criteria of selecting that particular data point. So what I'm going to do is I'm going to pick all those data points, all those genres which have at least 100 movies being attached to it, and then I'm going to create a trained data set as well as validation data set, and using this particular method where I'm going to do a sample by but grouping by genres so that I have the relevant sample being available based on the distribution, correct? So what I'm going to do is once I pick all the data points, pick all the movies, I'm going to create this validation data as well as the trained data. So as you can see here, the validation data shape, correct? If I'm going to just quickly run the command called validation data dot shape, it is going to give me about 39 data points, which I'm going to keep it as a validation data set, and I'm going to pick let's quickly check on the train data shape, which is roughly about 7708. So I've kind of filtered out all those data points which have less than 100 movies as per my criteria, and I'm going to take this data set forward for modeling purposes. So image data generated is an interesting feature within TensorFlow that helps you to load images in batches, and this is a blessing in disguise, because if you were to load each image on its own, your notebook is going to fail at some point in time. I tried doing that. By the time I loaded about 2000 odd images. My memory was already full and my notebook was killed. So there are going to be memory issues while dealing with images, and image data generator makes it all the more convenient to stream images from the directories. So that's what we are going to do here. We are going to create something called a train data gen and valid data gen using the image generator, and we are going to rescale the images by 255, and we're going to specify the target size of each of the image that we are going to load as 200, irrespective what the source image is. And then we're going to define two variables called the train generator and the valid generator. And as you can see, I'm feeding in the data point or the data frame directly inside the flow from data frame, and I'm giving the path to that particular file using the temp directory where I have stored all the movie posters. And I'm going to give the file name and the genre, which is the respective column names. I'm going to specify the batch size is 50. And the class mode is categorical because we are going to predict it's a multi-class classification, and hence it's a categorical. And we are going to give the list of classes, correct, which is a data set that we prepared a few minutes ago. And that is going to give you the list of classes given this particular data set. And similarly for validation valid generator also, we are going to give the validation data pointed to the same temp directory where all the movie posters are stored, and the same configuration as before. Once we define the train generator and the valid generator, once we run it, we will be able to see that it has found about 7,708 validated image file names belonging to 9 classes. And similarly for validation, it has found 39 validated image file names belonging to 9 classes, because that's what we have, 9 classes. Remember, we filtered out a lot of these classes because we didn't have enough data points to kind of do the training part of the equation. Now what I'm going to do is I'm going to define some of these global variables called the max pooling, filter size, node count, and dropout. And as you can see, I'm going to be a little aggressive. I'm going to give a max pooling of 4, filter size of 3, node count of 64, and a dropout of 0.3. Dropout is typically to kind of reduce the overfitting, and you can go ahead and experiment yourself by removing the dropout, and you'll see that you will very soon hit the issue of overfitting. And even after doing this, we have the overfitting issue, but we'll keep it aside for the time being. So what I've done is I've created the convolution on the pooling layer, and I've given the input, the variables as input inside the system, correct. And then I'm going to use a valid pooling, a valid convolution, which means as we convol the source image is going to reduce in size, correct. And you might as well try it with same pooling as well. So once we do the convolution and pooling, I'm going to flatten it out, and I'm going to create a dense layer as well, with 64 nodes, and then giving the activation as relu. And then since we are doing a multi-class classification, we are going to use softmax as a function, correct. And I've also given the length of filter, which is the number of classes that we are looking to predict. And I'm going to compile the model using optimizer, Adam, and categorical cross entropy as the loss, and I'm going to track these following 2 metrics. And you could look at the model.summary that we built earlier, and you could get a glimpse of how the data points, how the layers are laid out. And we have about 534,000 parameters in total that is going to be trained, correct. So remember, we don't, in pooling there are no parameters to be trained, correct. It's only in convolution. And then we are going to do the fit generator. The fit generator is fairly simple. I'm going to give the input as the train generator, which is the input that is going to be used for training the model, and I'm going to use validation data to be given as a valid generator, which we had created about 39 images, and I'm going to run this for 100 epochs. So let me run it, and once it finishes, we'll come back and analyze the results. So now the model .fit generator has already run, and you could see the training accuracy. Towards the end, 100th epoch is about 0.96, and the validation accuracy is roughly about 0.43, and it's hovering between zero point 0.5 and 0.43. And you could have a look at these data points, and it's really not going beyond that particular accuracy. Now, that could be the domain of the particular problem that we are looking at. Unfortunately, we can't do any image augmentation in this particular case because they are post images. But yeah, please feel free to try different configurations, and this is the best I could this is the best I could achieve in terms of the different configurations that I've been playing with. So here is a quick plot which gives you a plot between the training accuracy and the validation accuracy, and the training loss and the validation loss, and you could clearly see there is an overfitting, right? And the training accuracy constantly improves, whereas the validation accuracy doesn't improve beyond a certain point and keeps hovering around zero point 0.4, zero point 0.5, and so on and so forth. And here you could see that the validation loss with the number of epochs. I mean, if you were to take it about right after about 18th epoch, the validation loss keeps increasing, correct? Whereas the training loss kind of gracefully descends, correct? As I said, you could go and do your own experiment and come back to say how you solve this particular problem. I'll be more than happy to hear your version of your version that you took to in order to solve the overfitting issue. So this is the final code base that I'm going to play around with. So what I'm going to do is I'm going to pick this particular image, correct, and I'm going to randomly I'm kind of going to load this image, and I'm going to use the model.predict to predict what that image genre is all about. So as you can see here, I'm going to click on run, and then I'm going to choose this particular file, and so as I choose this file, the file is getting processed, and as you can see, I'm loading on 200 by 200, and the predicted movie is genre, and the actual movie is the predicted movie genre is comedy, and the actual movie genre is comedy as well. It does seem like kind of an Asian movie. So let's try with something which is very different, right? And this is the Lethal Weapon TV series. I'm sure Lethal Weapon as a film is already given as an input. So let's try this TV series as an input. I've downloaded this file, and let me show you how once I've uploaded it. So I've uploaded it, and you could see that the predicted movie genre is action, which is very true, correct? And Lethal Weapon is action comedy, correct? So let's try one more poster, which is Incredibles 2, so which I have also downloaded as part of my list. Right? You should either get Incredibles 2, so just bear with me. Yep, and I've got it, and I'm going to load it. So as you can see, the predicted movie genre is action. Animation could have been the more appropriate choice. But yeah, according to IMDb, correct? According to IMDb, if you just quickly Google Incredibles 2 IMDb, and this is something which it has not been given as a training input, correct? And then you could see that according to IMDb, it's animation action. Yeah, probably we need a lot more data points, correct? We probably need a lot more data points in the context of animation. If you were to look at the stats of the data points that we had probably about only 264 movies which are of type animation. Probably we need a lot more input as animation movies for us to kind of successfully classify them as animation. So it's a very interesting experience of uploading posters and finding out the respective genres. So as I said, please feel free to experiment on your own. This notebook is going to be available as part of this particular playlist. So please experiment, and please share your thoughts in terms of how you improved the performance of CNN. How did you, if at all, if you were able to overcome the overfitting problem, how did you go about solving the overfitting problem. I did try multiple options. I decreased the number of nodes. I decreased the number of layers. And I also decreased the filter sizes and so on and so forth. Correct? So I tried multiple options, but this is the best option that I could come up with. So I would love to hear from you as to how you went about solve this particular problem, and please share your experiments as well. So we have come to the end of this particular session. Thanks for watching, and if you like it, please click on like, and do subscribe to this particular channel. In the coming weeks, I'll be posting a lot more experiments that I'm going to play around with TensorFlow. I'm looking forward to hear your feedback on this particular experiment as well.